Okay, let's start the lecture. All right, good afternoon. Let's start lecture. Okay, so let's continue on the triple integral, and we're going to finish the triple integral today, okay? Just a quick review of what we learned from previous lecture. In the previous lecture, we learned how to evaluate triple integral in Cartesian coordinate. So basically, the definition of triple integral is if you're giving a region D and a function f of xy, and which is defined over this region D, then the triple integral basically is this one. Okay. The mathematical meaning of a triple integral we illustrated in previously. You could if this f function here represented the density. Sorry.
The last E in the sequence was dz.
Oh yeah. Good. So if this is representing the density, then this whole thing basically represents a mass of this region D, right? We have shown a couple of examples of evaluating it in Cartesian coordinates, and there is one example that I showed. Basically, you will have some difficulty using Cartesian coordinates, so which we bring this cylindrical coordinates into the picture. So cylindrical coordinates is essentially an extended version of the polar coordinates from 2D to 3D. Given a point P in xy coordinates, xyz coordinates, we can use another set of variables r theta z to express its location. So here's the definition for r theta z. So you drop the P, okay, project the P into the xy plane, then connect the origin to that projected point in here. Then the distance from here to the projected point is r. Okay, so know the definition very well, what the r and theta represent. And theta is the angle starting from the x-axis to where the projected line is. So this is theta. It is always positive if it's counterclockwise. If it's negative, if it's clockwise, it'll be negative. Okay, so that's theta. And z, there's no change. So z is also this z component of this Cartesian coordinates. So that's r theta z. So apparently, if we connect the x, y, z, okay, using the polar, so x equal to r cosine. See, this is r times cosine. You get x here. And r times sine, you get the y. And z equal to z, that's the z, right? So then in cylindrical coordinates, so what we do is we can replace the x, y, z here for this function f using r cosine theta, r sine theta, and z. So you will get the function of r theta z. And then the dv, okay, which is dx, dy, dz, okay, because of this transfer, basically it's a change of variable. The dv will become r dr d theta dz. Okay, just like a polar, it's this, but now you have a dz here. Okay, so using Jacobian, you can easily show that this transformation from here to here, and you can also refer to the lecture notes. Basically, there's a drawing using basically approximation what the dv is in the polar coordinates. Okay, yeah. So now let's continue the example that we started from previous lecture. Basically, this is an example that we started here. There are two surfaces, okay? So region D, so we give this region D at here, is defined by two paraboloids. So region D is between z equal to x squared plus y squared and z equal to 4 minus x squared minus y squared. Okay? So that's region D. As I illustrated in the first lecture, z equal to x squared plus y squared, we know that it's a paraboloid pointing upwards, which is the green one. Okay? And z equal to 4 minus x squared minus y squared. So if I don't have a 4 here, if it's negative, basically it's a paraboloid, the green one, mirror it about the xy plane. And then you have the 4 at here, because then lift that green one, the mirrored one, up 4 units. So you get this yellow one in here, the blue one in here. Okay? Yeah. So altogether, you have this region sandwiched between the two surfaces, and between there, that's region D. Okay? Yeah. So what we need is we want to calculate what's the volume of this region D at here. So it's pretty simple, right? Yeah. So calculate the volume, if you remember, basically, which means all you need to calculate is this triple integral. So in other words, the integrand at here is basically just 1, right? So f of x, y, z equal to 1, essentially. Okay? Yeah. So if you wanted to evaluate this one using Cartesian coordinates, you can do that. Actually, it is doable. Okay. However, it's basically not as easy though. So maybe what we can do is let's try just lay out this integral limits if we wanted to do it in Cartesian coordinates. Okay, and then we can look at the cylindrical coordinates. Okay, so let's say maybe the first method. Okay, let's say using Cartesian. Okay, Cartesian method, Cartesian coordinates. So if I use Cartesian coordinates, remember the steps, right? So you've got to follow steps here. First step is sketch this region D, which the question sketched for you already. Okay, and then you determine the order of integration. So the order of integration, we probably, in this case, let's try this dz, dy, dx. Okay, so this is order. Once your order is determined, then we sketch the shadow of this region D in xy plane, basically in the last two variables, which is xy in this case. Okay, so in this particular case, when you drop this region D or project it into the xy plane, you will see that it's actually a circle. It's a circle here. So basically, it's the projection of this intersected, okay, this region at here, okay, this curve, and that's what this red line in here. So that essentially brings the question, okay, so what is the equation of this curve at here, or the circle? Why is it a circle basically? Okay, how do we get intersection between the between these two surfaces? Okay, yeah. So how do we get that information though, right? You got two surfaces, and this red part at here is the intersection of the two surfaces. So what's the common things between the two surfaces at here? What's in common between the two surfaces at here? The z is all the same, right? So at here, the z is the same, basically, which means you have the two surfaces. Z are the same. So you let this one equal this one, right? So let me write it down here. Intersect. I don't know how to write English. So intersection of this and this. Okay, so that basically means x squared plus y squared equal 4 minus x squared minus y squared. Okay, so simplify this. We get this one bring up to the left. We got 2x squared plus 2y squared equal to 4. So that basically it means it's x squared plus y squared equal to 2, right? Equal to 2. Now this is the circle, right? This is the intersected circle, okay, or the bow at here. And it's a circle with a radius of what? 2 or root 2, right? Careful with that, okay? Okay, so you can label the bottom circle here is x squared plus y squared equal to 2. Okay, that's the circle here. Okay, so then we can start finding the limits for this z, y, x, right? Yeah. So if I try to find the limits, Remember the steps we follow, right? We start, basically I'm integrating with Z, so I'm starting from any point inside this region here, so any point inside this region, then you draw a line, okay, in the vertical or in the positive Z-axis direction, okay? So you will bump into this region D with the first contact and the exit at the second contact, right? That's the line that you draw it here. So the first contact to the XY plane give you Z mean. The second contact location give to the XY plane, right? That Z component give you the Z max. Okay. So the first contact basically is at the bottom surface, and the second contact is on the top surface. So basically, that means my Z mean, right, equal to the bottom surface, which is bottom surface is this one here. So Z mean is basically S squared plus Y squared. And then Z max is the top surface, and which is this one here. So that's essentially is 4 minus x squared minus y squared. So that's Z mean and Z max, right? Why is it a variable? Because if you choose a different location, you draw it, you end up with a different Z mean and Z max, right? But it's always on the bottom and the top surface there. Okay, so once you've done the first step now, the second step is for dy at here. So what we do is we draw a line in the positive y-axis, right? Positive y-axis. So this is a 3D at here. So I'm not really sure. Oh, this is y at here. So this axis is y, and that axis is x. Okay, yeah. So it might be good is what you can do is you can just simply draw the bottom circle. Okay, in the planar case, this is x, this is y. So x squared plus y squared equal to 2, right? And that's basically that's the region we're going to work on to find the y mean y max and x mean x max. And because this is a shadow, so within the shadow, okay, see this is where the starting point is. So you can draw an axis, okay, or line in the positive y-axis direction. Then the bottom contact, the first contact is the y mean, and the top contact is the y max, right? Yeah. So the first contact is at the bottom of the circle, and top contact is the second contact is the top of the circle. So apparently, from the equation, your y mean is what? 2 minus x squared is negative here, right? And your y max is positive 2 minus x squared. Okay, so first contact, second contact. Okay. Then the last step is easy now. So you sweep this, the blue line right here across this whole shadow, right? Across this whole shadow, and find the x mean and x max, the sandwiching bounds this shadow here. So apparently x mean is at here and x max is at here. So x mean equal to negative root 2 and x max is positive root 2. Alright? Yeah. So this is the three set of limits for x, y, z. Okay? And then all you need to do is plug it into the integrals that are here. So dz, dy, and dx. Okay? So z is x squared plus y squared to 4 minus x squared minus y squared, and z is the y is this. Okay, and x is this. Okay, yeah. So that's the layout of this calculating this volume if we decided to use Cartesian coordinates, right? Yeah. So bottom line is you will see, oh, the first one is pretty good. There's nothing there, so this integral just the top limit minus the bottom limits here, right? But then when it comes to the second one here, now that's things we're getting out because you got a square root here, right? So when you plug in the square root into the integral, you can imagine there's basically things getting complicated. Okay, yeah. So basically, evaluating this one here, trust me, it's gonna be forever. So this is why let's try the cylindrical coordinates. All right? Yeah. So this is difficult. Okay. Now, if I try cylindrical coordinates, now remember the idea here. Okay. The idea is integration is to integrating over the region D, meaning you want to sweep through the region D without redundancy. Okay? Yeah. So just like a Cartesian here. Now let's do this. If I'm going to integrate using cylindrical, basically we're going to sweep through the region D using this r theta z and here. Okay? Yeah. So I'm going to write it down here. Evaluate using cylindrical coordinate. Okay. Yeah. So just like the Cartesian coordinates, first step you draw everything, you sketch the region. Now what we do at here is we're gonna also have to determine an order of integration. Okay. So technically you can also have different combinations. You see here you can integrate the dr d theta dz like this, or you can integrate dz dr d theta, or the other way d theta dr dz. Right? Yeah. But typically for cylindrical, often in time, we integrate using dz first will make things easier. Okay, not necessarily all the time, but typically dz first will be more convenient. Okay, and then dr d theta. But I'll show you if I do the other way around though. Okay, so for now, I'm gonna say the order is dz, dr, and d theta. Okay, so let's try this one here. If I'm going to integrate to dz, dr, d theta, so basically you see the last two variable is r and theta, right? Is r and theta. Now if you see the r and theta, where's r and theta? R and theta is all within where? This xy plane, right? So this is basically, if this is the order we're integrating here, so essentially this means we're going to, just like the Cartesian xyz, we're going to sketch the shadow in the xy plane. Okay? Yeah, because the shadow in the xy plane will eventually determine this r theta limits. Okay? So if this is the order here, so basically that means we sketch the shadow, okay, in xy plane. Okay? And that's essentially the r theta plane there. Okay? Yeah. Okay. So there's no change here. This is the shadow. Basically, it's the circle, right? There's no change in terms of sketch. So now comes to the steps of finding z, r, and theta limits. Okay, so bear in mind of this. Sweeping idea here. Okay, yeah. So what you do is starting from origin. This is origin in here. Okay, starting from origin of this x, y, z coordinates. Then you draw. Actually, sorry, you don't have to start from the origin here. Starting from any point inside this shadow or the projection of the region D, then we draw a line in the positive z-axis. So that basically is the same thing as the x, y, z Cartesian coordinates there, right? Yeah. So draw it, okay, in the positive z-axis. Then you bump into the region with the first contact and the second contact. Was that right? Yeah. Okay, so we're on here. So draw in positive, okay, z-axis, okay, yeah. First contact, give the z mean, and second contact, give z max, okay, yeah. So the same thing. However, okay, the difference comes from here. So z mean, as we in previous step, what's that mean? It's x squared plus y squared, right? But we decided to evaluate using cylindrical coordinate, not x, y. So what do we do with x and y then? We replace that with the r cos and r sine, which is r squared. Okay? Yeah. So that's z mean. And z max do the same thing. So 4 minus x squared minus y squared. So you do the same thing, I guess we get what? 4 minus x r squared. Okay? Yeah. So that's z mean and then z max. No difference in terms of, but it's the difference is, remember, you could convert the x and y into the r and theta, right? If there's a theta, you put it there, but in this case, there's no theta. So the second step is to find r limits. So to find r limits is, here is where you started basically to draw that first line, right, across the region D. Then what we do is, in this second step is, start from origin. Start from origin of this coordinate system, okay, and draw, okay, a reading lines across the shadow. Okay, so this is the shadow here. So draw reading lines across the shadow. Okay. The first contact between this reading line and the shadow give you R mean. And the second contact between this reading lines and the shadow give you the R max. Okay? So remember, this is the draw within the shadow here, or within the xy plane here. Okay? Yeah. So guess what do we get? R mean is 0. R max is √2. Right? Yeah. So let me write it down here. So in the shadow, okay, draw a reading line, okay, starting from origin, okay, across the shadow. Okay, yeah. So the key is in the shadow, okay? You're not drawing anything in the 3D space, it's basically in the XY plane, okay? To draw that reading lines. First contact give you R mean, and second contact give you R max. So in this case 0, and then R max is 1. Okay? So if I go back here, let's consider that idea of sweeping, right? Idea of sweeping here. Imagine what's happening here, right? Your first step, we swept from here to here, right? The first step. Okay? Second step, you're basically moving this line along the direction of this R here, the reading line, the R. So when you're moving this line along this direction, that sweep, guess what's going to happen? You're going to basically end up with something like this, right? After this sweep. The second step. That make sense? See, the first one, you cut the region with just a single line there, right? And the second one is, you're going to move this one. Basically, imagine you're going to move this one across this whole region along this direction. Okay, along this direction. As it's moving, this line, the length should also change, basically, okay, according to the region D. So you're going to essentially end up with some kind of a shape like this, right? After the second step. Does that make sense? Yeah. So guess what? Sweeping. In the last step, if I want to create this region D, what should I do? I'm going to have to sweep this cross section by how much degree? 360 degree, right? Around the z-axis. Then you create this region here. So you must play, you must use SolidWorks. So how do you create a sphere in SolidWorks? What do? Huh? You have to create an axis of rotation first, right? And then you have to create what? A cross section. Then you sweep around the axis of rotation about a certain degree to get the objects, isn't it? Right? So that's the idea. Okay, we'll use this idea about the spherical coordinate shortly. But this way, you basically sweep through this region D. Okay, so that's the last step. So last step. Okay, so sweep. Okay, sweep this reading line. This reading line here, okay? Sweep this reading line, okay? across the shadow. Okay, sweep the region across shadow. Find the boundary. Find the boundary sandwiching this shadow area. Okay, for theta mean and theta max. Yeah.
Wouldn't R max be the root 2?
Oh, root 2, yes. Good point. I'm using. Well, that's why I make some wonder. Yeah, root 2. Thank you. Excellent. Somebody said 1. It's not my fault. Somebody said 1 here, so I just put a 1. Okay? Yeah. So sweep this across the reading line, find theta mean and theta max. Okay? Yeah. And in this case, theta mean is 0. Theta max is 2 pi. Okay? Yeah. So that's the steps finding the limits. All right? Yeah. Oh, you mean I'll put R here? Yeah. Absolutely, yeah. What I'm trying to say is, I mean, I don't put it here, but yes, you don't get rid of the R for sure, right? But here I'm just trying, this is going to be the order how you find the limits here. Yeah. So if I put it back, 3 limits, dz first, and then rdr, this is why we don't get rid of the R, and d theta. Okay? So dz, as we find, is r squared to 4 minus r squared. And for r limits is 0 to root 2, and theta is 0 to 2 pi. Okay? Yeah. So this way, you know, you have a unique, basically, sweeping through the region D, okay? And no redundancy. So let's try this integral out to see if there's any difficulty with this one in here. Okay? Okay, so first integrate is with respect to the z. So the higher limit minus the lower limit. So 4 minus 2r squared, then r dr and d theta, right? R dr d theta. Okay. Now, right from here, you actually can simplify the situation a little bit, because you see the inner integral here, right? This one here. And no matter whether it's the integrand here or the integral limits, we don't see the what? We don't see the theta variables. Is that right? Yeah, there's no theta variables. So in other words, whatever coming out of this inner integral right here, there's no theta, right? There's no theta. And there's going to be some kind of constant, but there's no theta. So when it comes to the last integral, the theta is basically whatever this 2 pi minus 0, just a 2 pi is. That makes sense, right? Yeah, so this is essentially just a 2 pi multiplied by the results of this one here. Okay? Yeah. And that's also a pretty easy one. So 4 minus 2r, which is what? 4r squared. I guess we're going to have to put a 2 out of here. 2r squared minus 2 over 3r cubed, and 0 to root 2. Is that right? Oh, no, sorry. This is actually what? Is that right? Yeah. Good point. Okay. So, plug the r into it. I think you would get 4 pi. Okay. So that's the way. So this is much easier, right? It's much easier steps to find this integral results. Okay. Any questions? Yeah. All good. Okay. So let's take a look at a couple more examples. Okay. Let's take a look at this one here. Okay, so z equal to square root x squared plus y squared. Okay, x equal to this. What is the, so this one here, I think we learned it. This is a cone here, okay? This is a cone. And this is the cone, looks like this, an inverted cone. Okay, this is a cone. And that's the Cartesian equation expressing this, describing this cone at here. So, what will be the expression in cylindrical coordinates to describe the same cone? You see what I'm saying, right? See, the idea is basically, here is a circle. Okay, here's a circle. So how do I use the polar coordinates to express this circle? R equal to 1, right? R equal to 1. So R equal to 1 is this circle. So same thing. This is the cone here in Cartesian expression. Then in cylindrical coordinates, what will be that corresponding expression? Z equal to R. Yeah. So because what do? You plug the x and y with, right? Basically z equal to r squared cosine squared and r squared sine squared, like this, and you end up with r at here, right? So z equal to r is the cylindrical expression at here. Okay. Yeah. Now, in the next step, okay, in the next one here, we'll have another set of what's called spherical coordinates. Okay, spherical coordinates. So let's just to set up for that but we'll talk about the next here. So let's look at this situation in here. Okay, if I starting from here, okay, starting from here, and then I draw a line, a straight line. Okay, I draw a straight line along the surface of the cone. Okay, doesn't matter where. You can draw anywhere, okay? Just draw a line along the surface of the cone here, okay? Up to the edge like this, okay? Yeah. Is that good? Yeah. Now, ask yourself, what's the angle, okay, from the z-axis to the line that you just draw here? What's the angle from here to here? So let's call that angle is phi. Okay, call the angle. Somebody said already, which is what? 45 degree, right? So why is it 45 degree? Well, let's do this. Let's pick a point. Okay, I pick an arbitrary point. Just maybe it's too small here. Let's pick a point. If I drop the point to the xy plane, okay, which is here, right? Which is here. Then I'm gonna connect, the origin to the projected points like this. Okay, yeah. Okay, so according to the cylindrical coordinate definition, what's this portion? It's r, right? It's r. And according to the cylindrical coordinates from here to here, what's this? It's z, right? It's z. But because this is a cone, and in our case z equal to r, so this is basically r here. So you see, if you look at this below small, but if you look closely, this is a 90 degree. So what do we have? Here, here, here. This one, it's a right triangle, right? It's a right triangle. So basically, you have a right triangle here, 90 degree. If this is definition phi, so this must be phi here too, right? And this is r, and this is r. So guess what? The phi and this phi must be 45 degree, right? 45 degree. Okay? So this is why phi is 45 degree here. Okay, so let me extend this idea to slightly here. How about a cone of this? What if I give you a cone of this? What if the cone is z equal to 1 over root 3 root x squared plus y squared? Then what will be the cylindrical coordinate expression for this cone? Okay, it's r, right? How about the phi angle? If I say this is a phi angle here, what will be the value for this phi angle? So you should try this. This is R now. This is R, and this side is not R anymore. This side is actually become 1 root R. So you have R at here, and you have this side is 1 over root 3 R for the Z. And this is a phi, right? This is phi. So what's the phi angle? So tangential phi equal to R over this and root 3, right? Root 3. So phi is 60 degrees. Okay? Yeah. The point is, you can tell people Z equal to R, meaning it's a cone. Now if somebody say, okay, I'm defining a phi like this, and say phi equal to 45 degrees, so you two actually are saying the same thing. Okay? And if somebody says phi equal to this angle, so you're actually talking this way here. Okay? So the reason is because I draw the arbitrary line here. It doesn't matter where you draw this red line here. The phi angle is always the same thing, given this cone equation, right? Yeah. Okay? So it's a different perspective. What I'm trying to say is it's a different perspective of this same geometry. Okay? Same geometry. So to extend this slightly, if there is an arbitrary cone equation, Z equal to A square root x squared plus y squared, then the cone is AR, Z equal to AR. And the phi angle will be what? What will be the phi angle? This is R, this is AR, and this is the phi. So tangential phi equal to R over this, so it's a tan inverse, what? 1 over A. Okay? Yeah. Is that good? Okay? Yeah, bear in mind this phi angle here, because shortly when we talk about the spherical coordinates, we'll have this new variable phi defined. Okay? Yeah. How's the phi defined? Just reinforce. Phi is defined an angle starting from the z-axis to where this reading line is. Okay? So this reading line is a line starting from origin through a 3D space. Okay? Yeah. So this is Z. That's the line. Okay, that's how you get the phi angle. Okay, so let's see another example here. Let's see. Yeah, you know what? I'm gonna skip this example here, and then if I have time, we'll come back to this. Okay. Yeah. Let's look at the next topic. So the next topic is basically what I just mentioned. In 3D space, there's another set of variables that come into handy, which basically is called spherical coordinates. Okay, spherical coordinate. This is a pretty useful coordinates, particularly for civil engineers. When you're dealing with GPS, when you're dealing with the location kind of a system. So I'm going to draw a 3D space, 3D Cartesian coordinates at here. Okay, and this is the point P that we can locate using x, y, z. Okay, yeah. And then in cylindrical coordinates, what we do is we drop that into the xy plane, and this is r, and this is theta, right? This is theta. Okay, yeah. Okay, so now in spherical coordinates, Okay, so we define two new variables. Okay, actually, yeah, based on this drawing in here. First, let's define a so-called rho, and that's the distance from origin to where point P is. Okay, so that's the rho variable. And then we define an angle starting from the z-axis to where this OP vector is, and that's defined as the phi angle. Okay. Remember, you gotta be very clear about the definition. Okay, so rho is basically absolute value of OP. Okay? Yeah. And phi is angle, okay, between z-axis and OP. Okay, and OP. And this is always a positive direction here. Okay. As a matter of fact, okay, as I'm going to show you, the phi, okay, is constrained to be between 0 and pi. Okay. Yeah, I'll explain this shortly. But for now, just remember, phi cannot be more than 180 degree, and cannot be a negative, or cannot be less than 0 degree. Okay. Yeah. That's fine. And the last variable for spherical is the theta, which is this one. Okay, which is this one here. So that's basically rho phi theta define as this so-called spherical coordinates. Okay, yeah. And for theta, the possible range for theta is 0 to 2 pi. That's a possible range of theta. But more thing, I think you need to be careful with this phi here. Okay, don't give it an angle. Yes. Yeah. Y 0 to pi, right? I can't explain it right now, but I'll explain it why this is one using an example later. Okay, this basically has something to do with how you sweep through the objects. Okay, yeah, and you have to sweep through without redundancy, essentially, right? Yeah. Okay, so rho phi theta, bear in mind I'll explain this, okay, can define a location of P, okay, equivalent to this x, y, z. So equivalency, essentially, let's take a look at what's the connection between Cartesian coordinates x, y, z and this spherical coordinates rho phi theta, right? It's rho phi theta. Okay, so what we can do is we can look at this geometry over here. Okay, the geometry here. So first of all, this is x at here, okay, and that's y over here. So what is x equal to? We learned x equal to what? R times cosine theta, right? R times cosine theta. Okay, so what about the r? If I want to express the r using rho phi, what would that be? This is rho, and this is phi. R is rho what? Sine phi, exactly. Okay? So from here to here, that's the first connection between Cartesian and spherical. And the next, y is r sine. So replace the r with rho sine phi. So that's the second expression. And the last one is z. And z, this is z here, right? This is z. So basically it's what? Rho times cosine phi, right? Rho times cosine phi. Yeah?
What's your y supposed to be? Like rho sine theta cos theta?
Yeah, so, okay, rho sine phi give you r here, right?
Yeah.
Then r, this is theta. R sine theta give you this y at here. Sorry, what's going on here? Yes, oh, it was, yeah?
Yeah.
Yeah, thank you. Yeah, I got a flu shot, so I think it's feeling dizzy. Is that good?
Yeah.
Thanks. Good. Okay, so the three equations in here establish the connection between Cartesian coordinates and spherical coordinates. Okay? Yeah. So in terms of basically, sometimes if you're a civil engineer, so what you do is, maybe let me just quickly go over some of the concept here, right? And when you're dealing with the Earth, GPS, we sometimes have different names for those variables. So let's say if I have the Earth system over here. Okay, so that's a sphere, right? That's a sphere representing the Earth. So remember some of the common things for this is x, y, and z. Okay, this is x, y, z. For this particular line, for this particular circle, this one here, okay, and basically this one is called 0 degree longitude. Okay, 0 degree longitude. So if you move this, if you rotate this circle about the z-axis, then you will end up probably somewhere else, right? You probably end up with somewhere else, and basically, and then basically what happens is that's the theta angle. So when you rotate about the z-axis, you have this so-called theta angle there, right? Yeah, theta angle. And this 0 longitude is what we call the prime meridian. And that circle, actually in on Earth, it passed through which city? Greenwich, right? Yeah, Greenwich. Okay. Yeah. So if you rotate that circle to this is east, and this is west. Okay. Yeah. So then basically, when you rotate it to the east, you get what we in convention we call that a positive theta angle. Okay. Yeah. So that's essentially it's a positive theta representing a longitude, right? Longitude into the east side. If you got a negative, let's say a negative 45 degree for the theta, and that's basically it's a longitude rotating to the west side there, right? Yeah, it's longitude. And then if you have let's say, giving a point on the sphere, okay, so from here to here, that's the rho, right, according to what we defined. Then on the Earth, there's actually the name for the rho is actually what? Sorry, the rho is actually called altitude, right? Altitude, okay? Yeah. So the rho is called altitude. Then the theta, which is actually called azimuth, right? Called azimuth. Okay. Yeah. Yeah. Was that a new? It is, huh? So now, if you have the phi angle at here, right? This is the phi as we defined using spherical coordinates. Okay. Yeah, this phi. Now, so in GPS, the complements of the phi angle, this portion is called 90 degree minus phi, apparently, right? 90 degree minus phi. So the 90 degree minus phi is actually called elevation. Okay, it's got an elevation here. So the elevation, there's one elevation to the north side, and there's another elevation to the south side here, right? So when you look at the GPS coordinates, there's always an n certain degree, or s certain degree. So basically that tells you there is another circle passing through this point. So this circle is what we call the latitude, right? The latitude. So this angle here tells you the latitude, basically. Okay? So this one here, latitude. Okay? So that's the connection, okay? So if you're interested, you can take a look at very basic GPS, the coordinates, how it's defined, right? But it's all related to the variables that we just listed at here. All right? Yeah, good. Okay, so now let's look at the spherical coordinates and how do we evaluate triple integral using spherical coordinates. Okay? But before we do this evaluation, let's do a similar exercise as that cylindrical coordinates example. Basically, I'll give you a Cartesian equation, okay? And then we express this Cartesian equation using the spherical coordinates, okay? So basically, for the same object, right? Expressing Cartesian, and what will be the corresponding part, okay, in the spherical. Okay, so this one here, what is it? It's a sphere, right? It's a sphere. So if this is a sphere in spherical coordinate, what will be the expression? The same expression representing this sphere using spherical coordinates. Without doing anything, actually, is what? Rho equal to 1, right? Yeah. So we didn't do, you didn't do anything, just, because this is a constant radius for the sphere, so the rho equal to 1. Now, if you don't trust this rho equal to 1, of course you should. So what you can do is, you can substitute this x, y, z. So this is a typical process. Substitute x, y, z with the 3 expression in here. Okay? And then see if you get rho equal to 1. So you will, right? So I'm not going to exercise this, but let's do this one here. So this one. So x squared plus y squared plus bracket z minus 1 squared equal to 1. So what does this represent, first of all? Circle? Sphere, right? Translated in which direction? Z-axis by 1 unit, right? Yeah, so 1 unit, let's see here, with the radius of 1. So it's the same, it's still a sphere. But that's what the pumpkin looks like in my home. So this is a sphere like this one here, right? Yeah. So then the question is, what will be the spherical coordinates? What will be the expression using spherical coordinates for this sphere here? Okay. So what did I do? Remember what I said? I'm going to substitute x, y, z with the 3 expressions over here, right? Yeah. So let's do that. So this needs a little bit careful calculation though. Okay. So x equal to rho sine phi and cosine theta. Okay, that's x. And so x squared meaning rho square sine phi square cosine theta square. Okay. And y is rho sine phi sine theta. And then square square square. Okay. And z is rho cosine phi minus 1 squared equal to 1. Right? So that's the substitution, first step. So from here, you're going to have to rely on trigonometry identities to simplify this equation. Right? So let's see, how do I simplify this? Let's look at the first one here. What's the common factor? This is a common factor here, right? Yeah. So that is rho square sine phi square, and then you end up with the inside the bracket is cosine theta square plus sine theta square, which is 1, right? So the first 2 terms simplified into rho square sine phi squared. Second term here is this. So we're going to have to expand this one here, expand it out. So if we expand it out, what do we get? Rho square cosine theta square minus 2 rho cosine phi plus 1 and equal to 1, right? Equal to 1. Okay? Does that make sense? Yeah? So now simplification. So this one will cancel each other. The first 2 terms, common factor, is rho square. And then you end up with a bracket, inside bracket, sine phi square, cosine phi square. So basically, I end up with a co-rho square, right? And then this is a minus 2 rho cosine phi. This one is a gone, so 0, right? 0. Okay? The last step, this minus this, the common factor is rho. Inside, okay? That make sense? Yeah. So this guy equal to 0. So technically, mathematically, which means what? Either rho is 0 or this, right? But rho is 0, not possible, because this is a sphere. Rho is not 0, so you don't use this one. So the end results is this. Okay, is this. That makes sense? Yeah. Now, if you're interested, actually, as you're gonna see, is this. I'm gonna do this way here. Okay. If I draw a reading line, okay, across this sphere, okay, so I basically starting from here and draw a reading line across this sphere. It'll intersect the sphere somewhere here, right? Okay, yeah. So according to the spherical coordinates, what is the phi angle? It's the angle between where? Between the z-axis and this line here, right? So this is basically the phi angle. Okay? What's the length from here to here? That's rho, right? That's rho here. Okay? Now if I do this, if I connect this point, okay, so basically the top vertex of this sphere to the intersection point, from here to here, I connect these 2 points here. Okay. Guess how much angle is here? 90 degree. Why is it 90 degree? You know, when we do this, what do we do? When we do the polar, right? When we do the polar, remember, you know, you have a circle, right? And then you draw the line here, and then we connect here. We said that's 90 degree, right? Because it's within the circle. Because this point is within the circle here. And you connect any point to here, you know, that's basically a right triangle. Now, if you're talking about a sphere at here, how many circles? You know, you can always create a circle passing through the point here, right? You can always create a circle basically, and that circle will contain this right triangle. Okay. So basically, this is a right triangle when you connect the point to this contact point here. That make sense? Yeah. So if this is a right triangle here, and this is where's the phi? This is a phi at here. And how long is this hypotenuse here? This from here to here is 2, right? From here to here is 2. So look at this right triangle here. This is 2. This is phi. This is rho. So what does rho equal to? So cosine phi equal to rho over 2, right? Rho equal 2. And rho equal to same thing, right? Yeah. So basically, you see, this is arbitrary reading lines I draw here, and that actually is the fundamental first step when we're evaluating triple integral, and we will try to find the limits for rho phi theta, right? And I'll show you basically the first step is we're going to draw this line here across the region, okay? And then from the first contact, second contact to figure out the rho limits. Was that good? Okay, good. So trying another one here, okay? Yeah. Another example. Just get used to this change of idea, change of a perspective. Z equal to x squared plus y squared square root. as we just said, this is a cone, right? This is a cone here. And the cone in cylindrical, it's z equal to r for this one. So now what will be the spherical expression? Okay, the expression in spherical coordinate for this same cone. We actually did it already, right? Expression in spherical coordinate. So what do? We can try the approach in the previous example. I mean, actually, we did already. So this expression should be what? Phi equal to pi over 4, right? In the previous example. So let's try this. Let's substitute z with the three expression. The z with rho cosine phi, and xy with rho square sine phi square cosine theta square plus rho square sine phi square and sine theta square, right? Substitute the x, y, z with the corresponding expression for the x, y, z, the three expressions, okay, here. Okay. Then inside the square root, that give us a common factor, give us what? Rho square sine, okay, phi square. Okay. Now, remember the hard constraint on the phi is between 0 to pi, right? Between 0 to pi. So sine theta is this, 0 to pi. So between 0 to pi, sine is always greater than 0. So this thing here, rho is defined as the distance. So rho must be greater than 0 too. So this is basically rho, what? Sine phi, right? Okay. So two sides, the two rows cancel. Cosine phi over sine phi. So which give us tangential phi equal to 1. In other words, phi equal to, right, pi equal to 4. Okay? Yeah. So phi equal to pi equal to 4 represent the same cone as this z equal to square root x squared plus y squared. And z equal to r, same thing, represent this same cone right here. Okay? Yeah. Just in a different perspective, right? Yeah. Okay, so now let's talk about this evaluating here. Okay, so this evaluate the triple integral. So to evaluate the triple integral, what we need to do is, so let me write down the original triple integral. This is the original triple integral we're evaluating in Cartesian. And what we need is, we don't want to use x, y, z anymore. We want using this rho theta phi, right? Rho phi theta, doesn't matter, okay? So what do? We're going to replace this x, y, okay? We're going to replace the x, y with the three equations. 1, 2, 3, okay? Yeah. And then the deviator here. The deviator here will be changed to basically a new set of d rho, d phi, and d theta. However, there's going to be something at here, right? It's not going to be a direct change. Okay? Yeah. So the question here is, what is this question mark? We can use what? The determinant of that Jacobian, the change of variables. Okay? Yeah. So your guideline to create the change of variable of the determinant of Jacobian is the three equations, x, y, z. See, x is a function rho phi theta, y is a function rho phi theta, and z is function rho phi, there's no theta, but it's a theta. So your Jacobian basically is dx over d rho, dx over d phi, and dx over d theta, and dy over d rho, dy over d phi, and dy over d theta, and dz over d rho dz over d phi and dz over d theta. Okay? So that's the Jacobian here. And the determinant is the 3 by 3 matrix. Anyway, if you plug the these three expressions into this perfect derivative, a simple perfect derivative, you should be able to calculate. And then you calculate the determinant. What you're going to end up with So what you're going to end up with is rho square sine phi. Okay? Rho square sine phi. Okay? So what does that mean is basically, if you wanted to evaluate in the triple integral in spherical coordinates, then at here we gotta have this portion. Okay? Rho square sine phi at here. Okay, is that clear? Yeah, that's the change of variable from xyz to rho theta phi. And you can also look at the lecture notes. Okay, if you don't like your Jacobian, you can look at the lecture notes. There is a simplified version. Okay. So there's a simplified, basically use approximation idea. If you have a sphere, how do I approximate a box, okay, using spherical coordinates? And what will be the volume of the box? So you will end up with the volume of the box is rho square sine phi d rho d phi d theta, same as the one I just derived there, right? So the same thing. Okay, it's very simple. Okay, so yeah, by the way here, maybe you can try this. Cartesian spherical coordinates often in time can give you pretty weird shapes, very interesting ones if you plot them out, which probably are very hard to express using Cartesian. Like this one, rho equal to this, you end up with this so-called wrinkled sphere. Okay, this actually, when I look at the reference is actually from a medical journal. I'm not sure what he's doing there, but he's probably doing hard research somehow, right? He draw this one here. And if you change this phi to 4 phi here, nothing changed, this is 4 phi, then we get this so-called bumpy sphere. Okay, yeah. If you print that using 3D, it's a naturally Halloween orange decorations, right, on the door here. Okay, so yeah, try it out. I have the meeple code here, so you can plot it and see yourself, right? All right, so now let's try some examples here. Let's see, how do we evaluate this triple integral using spherical coordinates? Okay. Yeah. Let's try to find a volume of a ice cream cone. Okay, so the ice cream cone is basically, so this is a cut from rho equal to 1 by phi equal to pi over 3. So the ice cream cone is cut from this rho equal to 1 by this one here. See, that's quite simple here, right? But if I interpret this one here, rho equal to 1, as we just learned, is actually a sphere. And phi equal to pi over 3 is a cone, right? But not a perfect ice cream, because ice cream cone has a topping, and that is flat. So this is a cone, and this is a sphere. Then you cut it out, and you get this ice cream cone here. So if I draw it and illustrate this drawing it here. Okay. So here's a cone. Okay. Here's a cone here, and then you have basically a sphere. right? You have a sphere with a radius 1 here. So imagine that when you cut the sphere using the cone, so you basically end up with what? With this top one here and the bottom cone at here, right? Yeah. And this top portion is from the sphere. And in other words, if I draw this one here, let's see the intersection between the cone and let's exaggerate this portion a little bit. Okay, so here you have an intersected circle here, and then you have a cone, basically the portion from the sphere on the top, and the body at here is that phi equal to pi over 3. Okay, yeah. Now what we want is, what's the volume of this ice cream cone? Okay, yeah, that's the idea here. Find the volume. Okay, so just like the other integrals using other varied coordinate system, we have to determine on the order of integration first. Okay, the order of integration. So the order of integration, in terms of this one here, we normally what we do is we do this d rho first, okay, and then d phi and d theta. Okay, so we normally use this order. Not that you cannot use the other order, but this is probably more intuitive. All right, yeah. So d rho, d phi, d theta as the order. And when we do this d rho, d phi, d theta, okay, then what we do is we need to sketch this one here. We also wanted to do this, sketch the shadow, okay, in xy plane. Okay, sketch the shadow in xy plane, because that's going to help us finding the limits for the theta. Okay, finding out the limits of theta. And theta is defined in the xy plane. So in this particular case, you see this is the cone, and so the shadow got to be that intersection right here, right? Got to be the intersection. And that intersection happened to be a circle. Okay, happened to be a circle here. Is that good? Yeah. Okay, so let's worry about the radius of the circle, okay, next. But what we can do is we can actually, in this case, you don't even need to figure out the radius circle. Okay, you'll see why. Okay, yeah, but that's the shadow though, right? You know the shadow is basically a disk. Okay, so the next step is to find the limits of these three variables. Step one, you draw, like what I did actually, you draw a reading line. Okay, you draw a reading line, okay, from origin, okay, across the region D. Okay, across this region D. In this case, the region D is basically the cone right here, right? The cone. Okay, so let's draw that. Starting from origin, draw a reading lines across this region D, the green one. Okay, yeah. First contact give us the rho mean. Second contact give us the rho max. Okay, yeah. And second contact give us rho max. So apparently, rho mean is at this origin must be 0, and rho max is on the top surface, which is the part of the sphere, right? So rho max must be 1. Okay, must be 1. Okay, the sphere has a radius of 1. Okay, and then second part to what you do is you sweep this reading line. Okay, so sweep this reading line here. Starting from, always sweeping, when you sweep, always starting from the z-axis and across the region D. So you always start here, okay? You always start here. Then you sweep across the region D. Find the phi angle that's sandwiching this region D at here. Okay? Is that clear? So you see here, this is the reading line here, right? This is the reading line. So when you're sweeping, you're always starting from here. Then you sweep across this region D. So that the two boundary must be one is over here, one is over here, right? And what's the phi angle corresponding to for the two boundary here? For the first one, it's for the phi is 0. And for the second one, the phi must be pi over 3, right? So that's the limits here. So sweep the reading line across region D. Okay. Okay, the boundaries give us this phi mean and the phi max. I should see always, okay, always starting from z-axis to sweep, okay, to start the sweeping. So z mean is phi mean 0 and pi over 3. And the last step, okay, so the last step is, so if you drop this one here, if you drop this reading line into the xy plane, then you have this a projection, right, in this shadow, okay, in the shadow here. Then if you, the last step is basically sweep this line here, sweep this projected line across the whole shadow, find the limits for theta mean and theta max that contains this shadow, okay? So guess what? This one, when you sweep, because the shadow is the whole shadow here, right? There's a whole bunch of shadow, not a whole bunch, just one shadow across this 360 degree. So when you sweep, the theta limits is 0 to 2 pi. Okay, so that's the last step here. So sweep the projection of the reading line, okay, across the shadow. Okay, so theta mean 0 and theta max is 2 pi. Okay, yeah. So now you're ready to lay down this integral right here. So we're looking for is the volume, right? It's the volume here. So the volume basically dV equal to this, right? dV. But we're evaluating in a spherical. Spherical rho square sine phi d rho d phi and d theta. Okay, that's the layout. And there's no integrand. There's only one right here. Integrand is 1. And we figure out the rho is 0 to 1. We figure out the phi is 0 to pi over 3. And theta is 0 to 2 pi. Okay? Yeah. So the rest of the work is quite simple now. Okay? So it's a pretty simple integral. And we should end up with a pi over 3 for this integral here. Okay? Okay, so before I go, I try to answer the question for that why the theta, why the phi has to be within 0 and phi, 0 and what, pi, right? So this is how we can illustrate idea. Okay, so here's a sphere. Okay, here's a sphere. How shall we create this sphere? To create a sphere, let's do this, right? If I use any CAD software, maybe the steps I will do. Actually, the first step is not necessary. I will create a line segment. Is that okay, right? I'll create a line segment, and then I'm going to create a half circle. Basically, sweep this line from 0 to pi. And the last step is to rotate this half circle by 2 pi. Okay, now you think again. If the first step is to sweep the line from 0 to 2 pi, so we actually create a what? A whole circle, right? If the last step, if you sweep this whole circle still by 2 pi, guess what? You actually create the sphere twice. That make sense? So that's basically not a unique sweep. As a matter of fact, if you do that in SolidWorks, it'll create an error message. It cannot give you the sphere. Okay? Yeah. Any questions? Thank you.